In this unit on electric potential, we're going to introduce two new quantities. One is called electric potential energy, and the other, you might guess, is called electric potential. So you might ask, okay, why did scientists invent these two new quantities? Don't we have enough physical quantities already? I mean, if you think about it, we've been able to describe the motion of electric charges, okay, of charged particles by calculating the forces they experience in electric fields. As you will see, okay, these two quantities will not only help us describe electrostatic phenomena, okay, in the short term, but they're going to help us describe electrodynamic phenomena when we get to that point in the course. So the good news is this. You already have some familiarity, actually quite a bit of familiarity, with these quantities from the mechanics course you took, when you learned about energy. So in this slide, we're going to review some of the advantages of the energy approach over the force approach, when it comes to determining the motion of objects. In your course in mechanics, these objects were, baseballs, planes, trains, automobiles. Of course, in this course, these objects are going to be electric charges. So let's take a look at a review, a comparison of this force approach versus energy approach, and hopefully, you're not going to learn a whole lot of new information in this slide. So you recall the force approach, required that you knew the net force that acted on objects. So this probably started with a free body diagram. From that, you could apply Newton's second law to determine the acceleration of the object. And once that was known, assuming you had enough other kinematic information, you might be able to determine some other kinematic variable, like a final velocity or speed, a displacement, or even a time, involved in the motion of an object. The energy approach, well, that approach required us to define a potential energy function, anytime you had a conservative force. So as long as the forces involved in your problem were conservative, you could then define the potential energy function. And once done, you could then apply the law of conservation of energy, the conservation of energy principle, where you could equate the total energy of your system at two different points in time. And by doing so, extract information about the system. Now, the advantages of the energy approach, first of all, energy is a scalar quantity as opposed to force, which is a vector quantity. And working with scalar quantities is much easier when it comes to problem solving. Many of the complications in the dynamics problems you solved previously came from the fact that the directions of these moving objects changed, and that added a complication to the problem. Of course, when you use the energy approach, you're not going to be able to get any information about the direction that the objects move. Secondly, in practice, many situations arise where you do not have that much information about the forces, or the forces cannot be measured easily. Maybe the forces are too numerous, or they're too small to easily measure, or situations where the forces are not constant. When you think about it, a non-constant force leads to a situation where the kinematic equations don't apply, right? A non-constant force means the acceleration is not constant, therefore those kinematic equations are not valid. So, there's many reasons why in practice, when you're working with forces, there's complications to being able to solve your motion problem. Using the energy approach in electrostatic phenomena. So this is where we're headed here. And for some of these same reasons, Okay, we say that it turns out that the Coulomb force that we've been spending so much time talking about just so happens to be a conservative force. Therefore, you can define a potential energy function for it. Okay, we are going to introduce two scalar quantities to describe electrostatic phenomena. Okay, the first, as we mentioned, is what we call electric or electrostatic potential energy. Okay, the second is what we call electric potential. And as we will see, just as we saw in the case of mechanics, in the field of mechanics, okay, that this is very advantageous. These new scalar quantities are much easier to evaluate, okay, than are the Coulomb force, okay, or the electric field itself. Why? Okay, because force and field are vector quantities, okay, and they're much harder to evaluate. So like I said, you know, some of the information about directions is not available to you when you take this scalar approach, this energy approach. But if that is all that is needed, okay, in other words, if you do not need to know about, okay, the directions that objects move, okay, then this approach is generally much easier, okay, when it comes to problem solving. In this slide, we will very quickly review the concept of work, okay, what it means for a force to be conservative, okay, and how we define a potential energy function. So, starting with the concept of work, well, if we always talk about the work that is done by a force on an object. If that force is constant, okay, then the work can be found by simply evaluating the dot product of the force acting on the object and the displacement of the object. If, however, the force varies as the object moves, okay, from its initial point to its final point, okay, so we're talking about the case of variable force, and that's what this diagram illustrates. Notice that as our object moves along this curved path from point A to point B, the force is neither constant in magnitude or direction, okay, in which case we need to break up that path into small enough little increments such that these displacement vectors dr are so small, okay, that we can consider the force to be at least constant, okay, over that very small displacement, in which case we can calculate the infinitesimal amount of work done, okay, for each of those infinitesimal displacements, and then sum up, okay, all of those work contributions, simply add them up to get the total work done. So here we express work as a line integral, okay, for the variable force, okay, evaluated from our starting point, our initial point, okay, in this case A, to our final point B. Now, when we talk about a force being conservative versus non-conservative, okay, well, a conservative force is a force where the work that is done by the force on the object as that object moves between its initial point and final point, that work is independent of the path taken. And the way we can succinctly state this, okay, is we can say that the line integral, okay, for the work done by that force over any closed path is 0. And when you look at the diagram up above here, just to kind of see how what I'm showing you here translates, if the work done is independent of the path taken, then whatever path you take in going from A to B, a certain amount of work is done. Then we can say that if the force is conservative, okay, when you go in the reverse direction, that is, you take any path from B back to A, okay, then that amount of work will be exactly opposite, okay, the amount of work done from A to B. In which case, when you add up the work in going from A to B plus the work in going from B back to A, now you're getting the work done over a closed path, okay, and those two work terms will cancel, in which case the work done over that closed path is 0. So hopefully you can see why this is an equivalent statement here. And likewise, if the force is non-conservative, then the work that is done by that force, okay, between two, as it moves between 2 points in space, does depend upon the path taken. You recall, for example, that friction is a non-conservative force. You want to slide a box along the ground, okay, between 2 points in space. Obviously, the path taken is going to determine how much work is done by the force of friction. The greater the distance taken, okay, the greater the path length, the more work will be done by that force. So here we're saying that the line integral expressing the work done by that force, okay, over a closed path would not be equal to 0. Okay, why? Because the work will depend upon the path taken. And once, okay, you know that you have a conservative force in question, okay, for those special type of forces, you can define a potential energy function. And this is really, it was really important when we talked about gravitational potential energy in mechanics. It is equally important, as you're going to see when we talk about electric potential energy and electric potential in electrostatics, okay, that you do not forget about this negative sign. The change in potential energy of an object is equal to the opposite of the work done by the conservative force on the object as that object moves from its initial position to its final position. Of course, in the case of electrostatics, this object is almost always going to be a charge or a collection of charges. And we can write this quantitatively in the form of this line integral. We can say change in potential energy here, okay, is equal to the opposite of, okay, and we'll use a symbol F sub c to represent a conservative force. So this is simply the work done by the conservative force as the object moves, okay, between its 2 points in space, initial point to final point. All right, so given that review, okay, let's get to it. Let's talk about these two new quantities. The first quantity we'll introduce is what we call electrostatic, or sometimes just called the electric potential energy difference. And sometimes we use a symbol, capital PE for potential energy. I'm going to use a symbol capital U here, okay, to represent potential energy. So these are both very commonly used symbols. And as I alluded to in the previous slide, in the case of electrostatics, the object we're talking about in question here is going to be a charge. So let's assume that a small charge, which, okay, we can represent by Q here, moves from point A, okay, which I'm showing you here, okay, from point A, okay, to point B along this path I'm showing you here. In this region where there happens to be an electric field that is created by some charge distribution. Now, true, I'm not showing you what that charge distribution looks like. Okay, that's irrelevant so long as we know what the field looks like. And you'll notice here that the path is curved, the electric field is not uniform. And I'm showing you an infinitesimal displacement vector. I'm going to use the symbol, okay, ds for displacement. And the reason I won't use dr is because in many cases we're going to use the r to represent a radial direction. Okay, so to be general here, I'm going to use the s. I know that some texts use the symbol dl to represent a displacement vector. Giancoli does, in fact. I don't like that notation because when we talk about current distributions, when we talk about magnetism, the L's and the I's look very much alike, and it's easy to get them confused. So we'll stick with this symbol ds to represent an infinitesimal displacement vector. Okay, with that said, then here goes. In terms of the Coulomb force, we can say that delta U will use a symbol BA. That means the potential energy, okay, of our charge at point B minus the potential energy of the charge at point A, okay, is equal to, as we said, this is just the definition of potential change in potential energy, right? It is simply the opposite of the work done by the Coulomb force on the object, okay, on the charge. So this is simply the definition here. F sub E, recall, is the Coulomb force, and this takes into account the case if the Coulomb force is variable, okay, then we need to express the work done and therefore the change in potential energy as a line integral. Okay, in the special case, if we had a uniform electric field, and we will see that case, then maybe we can express the work and therefore the change in potential energy as a simple dot product of two vectors if the force is constant and the field is constant. But this is the more general description here. So given this, and you recall that the electric field, by definition, okay, is the Coulomb force acting on a test charge at a certain point in space divided through by the test charge. Okay, we said that once the field is established, then you can find the Coulomb force on any charge Q simply by taking that charge and multiplying it by the field, the electric field at that point in space. So we can, and we will more often express, okay, the change in potential energy that a charge experiences, okay, in terms of the electric field rather than the Coulomb force. So just substituting in, if the Coulomb force is just equal to the charge times the electric field strength here, and just making that substitution here for F sub E is Q times E, okay, then we have a similar expression for the change in electric potential energy. So given this, a few things to note about the meaning. Don't think you're going to really learn anything new here. Okay, first of all, well, this is important. It may not be new, but remember that Q can be positive or negative. Okay, it shouldn't be so big that it can affect the charge distribution in any significant way, thus changing the value of that electric field, but Q can be positive or negative. It doesn't have to be a test charge. Okay, it is important you remember to put in the sign of Q when you are evaluating the change in potential energy. Remember that delta U represents the change in potential energy. Okay, very often if your initial potential energy, you define a reference point or 0 point to be 0, okay, then your change in potential energy will simply be equal to your final potential energy in the problem. And since the change in potential energy is expressed as a line integral, okay, the value of delta U does not depend upon the path taken, okay, by your charge in moving from point A to point B, since the Coulomb force is a conservative force. So this is important because very often, okay, you've got to keep your initial point and your final point the same, but very often when it comes to evaluating that line integral, you are free to choose any convenient path you would like, okay, and very often there's, a more convenient path to choose than the actual path taken. And it makes absolutely no difference whether you use the actual path or a completely fictitious path, okay, the answer will be the same. And lastly, let's think about what you already know about potential energy and changes in potential energy, okay, and let's think about this. We know that positive charges naturally move in the direction of the electric field, right? Because this is how we define the field. Okay, we would say that the electric field is in the direction that a force would exist on a positive test charge. So we know that positive charges naturally move in the direction of the field. So when we look at our definition here, okay, let's think about this. If we have a positive charge such that Q is positive, okay, and the charge moves in the direction of the field, that means that, okay, the displacement ds and the field are going to be in the same direction, okay, so that we're taking the cosine of 0. What does that tell you about the change in potential energy? The change in potential energy is going to be negative, okay, times a positive number times a positive number. The change in potential energy will be negative. Well, that should make sense because, when a positive charge, okay, moves naturally, okay, in the direction of the field, it is going to lose potential energy. In the same way, when an object with mass moves naturally in the direction of the gravitational field, okay, it is going to lose gravitational potential energy. You can see here the opposite is true, that when you have a negative charge, okay, when you put in a negative value for Q, the negatives cancel out, okay, here, and you will find that the change in potential energy, okay, is going to be positive when that charge moves in the direction of the field. Okay, so in this case, that is synonymous with your charge gaining, okay, electric potential energy. All right, so now that we know how to calculate the difference in electric potential energy, okay, that a charge would have at two different points in space, okay, we're now in a position to introduce this new quantity, this related quantity that we call electric potential difference, symbolized with a delta V as opposed to a delta U. And if you're saying, that V, that kind of sounds like voltage, well, you're onto something. Okay, so in a sense, we can think about a difference in electric potential as being synonymous with a difference in voltage. So, okay, this is a new quantity. It has a definition, and by definition, it is similar but not identical to what we just described in the previous slide. That is the difference in electric potential energy. Okay, the difference in electric potential between 2 points in space, point A and point B, that is going to be the electric potential, okay, at point B minus the electric potential at point A, is nothing more than the potential energy difference between those 2 points divided through by the charge. So when you take the expression on the previous slide and you divide through by the charge, okay, notice what this leaves you left, right? Okay, that Q that existed in front of the integrand here, okay, in front of the integral no longer exists. So this is a definition. You got to memorize it. I want to point out here, okay, the independence of charge. And let's start by, okay, looking at, okay, two quantities that we're already familiar with. One quantity that we're already familiar with. So when I talk about a charge-dependent quantity, remember that we started our unit on electrostatics this semester by talking about, okay, the electrostatic force, the Coulomb force. And that clearly was a charge-dependent quantity. But when we talked about this related quantity called the electric field, okay, you recall, how did we get that? Well, the electric field was nothing more than the Coulomb force acting on a charge, a small test charge. We divided through by the test charge, so it became a charge-independent quantity. Okay, this is the same concept here in our discussion of these scalar quantities. When we talk about electric potential energy, okay, we said that the electric potential energy difference, okay, between 2 points in space, well, that was the difference in electric potential energy that a charge would experience between those 2 points in space. Okay, but now when we talk about this related quantity called the electric potential and an electric potential difference, okay, it is a charge-independent quantity. Okay, it, in the same way, electric field, okay, does not depend upon having any charge at those 2 points in space. So let's, okay, highlight this a little bit more here, okay, when we make this comparison here between an electric field and electric potential. So in the case of the electric field, we said that, first of all, it is a vector field. Oh, looks like you're hearing my son's Cocker Spaniel in the background coughing here. So sorry about that. I had to keep Gabby in this room today here. Okay, lovely. Thanks, Gabby. The electric field is a vector field. It's omnipresent, which means that it exists everywhere surrounding a charge distribution. So we said that the source charge distribution, okay, sets up this electric field at all points in space surrounding it. And that whether or not there happens to be any charge for that field to interact with, the field exists independently of whether there's any charge there to feel it, okay? If there happens to be a charge that exists at a certain point in space, okay, where the field is, call that a field point, well, then that charge will experience a force, okay? There will be a force exerted on the field charge if a charge happens to exist there. If no charge exists, the field still does. When we talk about electric potential, this is a scalar quantity. It is a scalar field. In the same way the electric field was a vector field, we can say that, okay, a source charge distribution sets up, okay, and the scalar field, we call that electric potential, at all points in space surrounding it. Whether or not there happens to be any charge there, okay, for it to feel, okay, the effects of this field, the effects of the scalar field. The field exists independently of the charge. But how do we interpret it if there does so happen to be a charge at that point in space? Well, then we would say that potential energy gets injected into that field charge, okay, if the field charge happens to exist there. So the existence of a charge in the scalar field, okay, we can think of as having potential energy injected into it, okay, by its existence. All right, so in this slide, we'll make a comparison to what we already know about gravity, that is gravitational force and gravitational potential energy, to these two new electrostatic quantities. So, okay, first of all, when we talk about potential energy, we can say that objects with mass possess gravitational potential energy due to their location in a gravitational field. In a similar way, we can say that objects with charge possess electrostatic potential energy due to their location in an electric field. See, this is a thing about field theory, okay? Regardless of whether it's a gravitational field, an electric field, a magnetic field, a nuclear field, we talk about the two nuclear forces. Field theory is field theory. So if you understand it for gravity, okay, then there's not a whole lot that is different when you substitute gravity with some other fundamental force. And in the case of gravity, when we talked about gravitational potential energy, okay, we said that by doing work on an object with mass against the force of gravity, as I'm doing when I push this object up the hill here, okay, moves the object from a region of low gravitational potential to a region of high gravitational potential and increases the gravitational potential energy of the object. So, okay, that's something you know. When you move an object up the hill, okay, from a region of low gravitational potential to high gravitational potential, you're increasing the gravitational potential energy of the object. Okay, it is virtually identical in the case of electrostatics. So let's take a look at an equivalent situation. Okay, doing work on a positively charged object, okay, take a little positive charge here, exert some sort of applied force on it, and notice that this charge, the source charge distribution is positive. So the positively charged object I'm holding in my hand here is repelled by the positive source charge distribution. So obviously, due to this repulsive force, I've got to do positive work, okay, to move that object from a region of low electric potential to a region of high electric potential. And when I do so, I increase the electric potential energy of the object. Okay, so hopefully you can see the similarity with what you already know about gravity. And lastly here, we'll take a look at this idea that potential energy, which we think of as stored energy, can be converted into either work or kinetic energy. Starting with the pile driver, okay, you know that objects with mass will naturally move in the direction of the gravitational field, okay, from regions of high gravitational potential to regions of low gravitational potential, okay, and when they do so, when they move from high gravitational potential to low gravitational potential, they lose gravitational potential energy and gain kinetic energy in the process, gain kinetic energy as they travel. It's exactly what's happening with the pile driver here, okay, when the string is cut, right? It's losing gravitational potential energy, okay, and that loss of gravitational potential energy, it is being converted into kinetic energy. Similarly, don't ask me what you call this, it's a fictitious arrangement here, but the idea still holds, okay, that positively charged objects naturally move in the direction of the electric field, okay, from regions of high electric potential to regions of low electric potential, losing electric potential energy and gaining kinetic energy as they travel. All right, in this slide, we'll consider a simple problem where we can plug in some numbers. So in this example, we're asked to consider moving a small amount of charge, okay, minus 10 microcoulombs of charge, in the direction of the uniform electric field between the plates of a parallel plate capacitor here. So I'm showing you the capacitor plates, the charges on each plate, and therefore the direction of the field, okay, which is from plus to minus. Okay, now Gabby is snoring in the background. I guess that's preferable to her coughing. Okay, always something with that dog here. Assume that the small charge moves 0.2 meters and requires a constant force of 0.5 newtons. So let's get a picture of this here. So we have our minus 10 microcoulombs of charge. Okay, and you'll notice that the minus 10 microcoulombs of charge, okay, it is a negative charge. So if we are going to move it towards the negative plate, okay, we're going to have to apply a force on it and do some positive work. And we're told here that the force that we apply is 0.5 newtons. So, okay, we're going to move it from this point here A to this point B here, and we're told that this is a distance of 0.2 meters. All right, so first we're asked to find out how much work is required to move the minus 10 microcoulombs of charge. All right, well, in this problem, we're told that a constant force of 0.5 newtons must be applied, okay, to move the charge from point A to point B. We know the distance traveled here of 0.2 meters. So using our definition of the work done by a constant force, applied force of, okay, 0.5 newtons, okay, magnitude of the displacement, which is just the distance in this case of 0.2 meters, and because that applied force is in the direction of the displacement, we're taking the cosine of 0. So we have to do an amount of work on the charge of 0.1 joules. Okay, now if it says what is the change in electric potential energy, well, here we have to remember our definition of electric potential energy is the opposite of the work done by the conservative force, not the applied force, but the conservative force here. Okay, the Coulomb force would be the conservative force acting on this charge. And although I did not draw it in the diagram, okay, the Coulomb force acting on the charge, okay, would be to the left, right? Because this is a negative charge, okay, the force it would experience here due to the negative plate as well as a positive plate would be to the left, right? It'd be repelled by the negative plate, attracted to the positive plate. The Coulomb force would be to the left. So when we take the opposite of the work done by the Coulomb force, okay, that is going to be exactly equal to the positive amount of work done by the applied force against the Coulomb force, which we already found to be 0.1 joules. What is the electric potential difference between these 2 points A and B? Here we're going to have to use our definition. Remember that, okay, the electric potential difference is simply the difference in the electric potential energy per charge. And remember that charge has a sign. So we showed that in moving from A to B, we are increasing the electric potential energy, okay, by an amount of 0.1 joules. When we divide through by the charge, which is negative 10 microcoulombs, or negative 10 to the times 10 to the minus fifth coulombs, this tells us that the change in electric potential between those 2 points, between points A and B, is negative 10,000 joules per coulomb. We're now asked to calculate the change in the electric potential energy of twice as much charge as moved from A to B. Okay, so I want to point out here that from our definition of electric potential here, okay, I want you to notice here that multiplying this equation here, both sides by charge, okay, we have a way of calculating the electric potential energy change if the electric potential difference is known. Okay, so here's the thing. The potential difference, the electric potential difference between any 2 points, okay, for a source charge distribution, in this case a parallel plate capacitor, that is going to be a constant. It makes no difference what kind of charge you move in between there. Remember, it is a charge independent quantity. So once you know the electric potential difference between those 2 points, it will always have that same value. So we can now find the electric potential energy difference for any charge that we want to move between those 2 points simply by multiplying, okay, that electric potential difference by the amount of charge. So here we've got twice as much charge. We're going from negative 10 microcoulombs to negative 20 microcoulombs. Okay, we multiply by the same electric potential difference of negative 10,000 joules per coulomb. And notice what happens here. Okay, that requires the charge, twice as much charge will experience twice as much, okay, twice the change in electric potential energy. So here I'm saying, 2 times the charge means 2 times the Coulomb force, twice as much work required to move it, okay, by the applied force against the Coulomb force, which means it's got twice as much electric potential energy, or would experience twice the change in electric potential energy. Now, okay, this is important here. If I asked you to calculate, okay, the change in electric potential, not change in electric potential energy, but change in electric potential if twice as much charge is moved from A to B, okay, well, let's do that. From our definition here of, okay, electric potential difference, okay, our electric potential energy difference we found from part 4 above is 0.2 joules. We divide through by the charge, okay, which is negative 20 microcoulombs. And hey, look what happens. The difference in electric potential is identical. Okay, it doesn't matter. Notice this value here is exactly the same as this value here. In other words, like we're saying, it is a charge independent quantity. Okay, moving 10 microcoulombs from A to B, okay, gave us this answer here. Moving 20 microcoulombs from A to B gave us exactly the same electric potential difference between those 2 points in space. So while the electric potential energy doubles, okay, in other words, the difference in electric potential energy between those 2 points in space, moving twice as much charge is twice as much, yet, okay, the change in electric potential remains constant. A charge independent quantity. So look, from my experience teaching this stuff, I can definitively state that the biggest source of error when it comes to calculating electric potential energies and electric potential differences is with signs. Okay, so in the next 2 slides, I want to look at some examples where we apply the definitions, Okay, that is definitions of electric potential and electric potential energy, okay, to various situations, to both positive and negative source charge distributions, as well as to both positive and negative field charges, okay, that are moved, okay, around in the vicinity of those source charge distributions. And I'm hoping that after doing so, okay, this will help you get a grip on all possibilities of signs, okay, and more importantly, hope that it will prevent you from making these sign errors. So let's take a look at these 4 scenarios here. Now you'll notice here that I've got, okay, little q here. This is what represents a field charge. Okay, big Q here represents the source charge distribution. And you'll notice that we have all different combinations here. Okay, all possible combinations of source charges and field charges here. And what we're going to do is we're going to move the field charge, little q, from point A to point B in all cases. And in doing so, okay, depending on the sign of the field charge, little q, or the source charge, big Q, okay, we're going to calculate the sign of the work that is done by the Coulomb force. Okay, once we know that sign, we can now calculate the sign of the electric potential energy difference, right, which by definition is the opposite of the work done by the Coulomb force. And then finally, we can calculate the sign of, okay, the electric potential difference, okay, for our charge distribution. So let's start by doing this here, starting with the top scenario here where the field charge is positive, the field charge that we're moving, okay, is positive, as well as the source charge distribution here, okay, is positive too. In which case, okay, the Coulomb force, we know that like charges repel, okay, the Coulomb force on our field charge will be to the left here. So let's think about it. If we want to now move this charge from point A to point B, notice that the Coulomb force will be opposite the displacement, okay, in which case we've got that cosine of 180 degree factor when we evaluate the work, okay, in which case the sign of the work done by the Coulomb force will be negative. And once you know that, then by definition, okay, the sign of the electric potential energy difference, by definition, is just the opposite of the work done by the Coulomb force, so it must be positive. And when we now calculate the electric potential difference, okay, we have everything we need, right? Okay, the electric potential energy difference, which is positive, okay, divided by the sign of the field charge, which is positive. So when you take a positive and you divide by a positive, you get a positive, okay, electric potential difference between points A and points B, point A and point B. So let's continue this process. We'll speed it up a little bit here. Okay, for our second scenario, our source charge distribution is still positive, but now the field charge that we're moving is now negative. Well, we know that a negative field charge would be attracted to a, okay, positive source charge, in which case the Coulomb force points to the right, in which case the work done as that charge moves from A to B is going to be positive. The work done by the Coulomb force will be positive, right? The force and the displacement are in the same direction. In which case, okay, the change in potential energy, which is just the opposite of the work done by the Coulomb force, will now be negative. And when we calculate the electric potential difference between those 2 points, okay, well, the electric potential energy difference we said is negative. The sign of the field charge is negative. When you take a negative divided by a negative, you still end up with a positive, okay, electric potential difference between point A and point B. Okay, for the next 2 situations, we're looking at a negative source charge distribution. So big Q is negative. Okay, we'll now start with the case where a field charge is also negative. Okay, knowing that like charges repel, the Coulomb force is to the left, yet the displacement is to the right. So that means that there's a negative amount of work done by the Coulomb force. The change in electric potential energy is simply the opposite of that work done, so it's going to be positive. And when we calculate the electric potential difference, okay, we have a positive value in our numerator for the electric potential energy difference. Okay, we have a negative value for our field charge, and a positive divided by a negative gives us a negative value for the electric potential difference between, okay, point A and point B. And the last scenario here, okay, okay, once again, our source charge is negative, but in this case, our field charge is positive, so they're attracted, opposites attract, in which case the work done by the Coulomb force will be positive since the force and the displacement are in the same direction. Okay, the electric potential energy difference will be negative. It's the opposite of the work done by the Coulomb force. And here, the electric potential difference, not to be confused with potential energy difference, but the electric potential difference, okay, is going to be a negative divided by a positive or a negative. So these are the values, okay, of the signs that we get for each of these quantities. And in the next slide, we will try to okay, form some conclusions about this. All right, so two very important consequences or conclusions, okay, from these four scenarios, these four examples we looked at, which will state in the slide. So notice here I just have the previous slide shrunk up a little bit so I can fit everything here. And the first question is this, okay, for a given source charge distribution, does the value of the electric potential difference between the 2 points A and B in question, does that value of electric potential difference depend upon the sign of the field charge? Okay, and hopefully you see that the answer is a resounding no. Okay, I'll state this in a second, but notice that when the source charge was positive, which is in scenario 1 and scenario 2, notice that moving closer to it from point A to point B, the sign of the electric potential difference was positive, okay, regardless of whether we moved a positive field charge from point A to point B or a negative charge from point A to point B. Likewise, when our source charge distribution was negative, when big Q was negative for scenario 3 and scenario 4, notice that moving closer to the negative source charge distribution from point A to point B, notice that the electric potential difference was negative in both cases, regardless of whether the field charge was negative, as in case 3, or positive, as in case 4. So writing this, we can say no. The value of the electric potential difference in this case, okay, or to be more general, let's say the value of the electric potential at a given point in space depends on the source charges only, not on the magnitude or the sign of the field charge being moved. Okay, and you can see here that when moving closer to a positive charge distribution, the electric potential increases. That gave us a positive difference in electric potential, a positive electric potential difference. Likewise, okay, when you move closer to a negative charge distribution, a negative source charge distribution, notice that regardless of whether you're moving a positive charge or negative charge closer to it, we can simply say that moving towards a negative charge, okay, causes, okay, the electric potential to go down. That gave us an electric potential difference that was negative. The second conclusion here, does the value of the electric potential difference between the 2 points in space depend upon the source charge distribution? Definitely. That is all it depends on. Okay, as we said, okay, when the field charge moved closer to a positive source charge distribution, the electric potential increases, okay, regardless of whether that field charge is positive or negative, and that's what I just showed you here. Okay, moving from A to B, the electric potential difference is positive, regardless of the type of field charge, the sign of the field charge, okay, that is moved. And likewise, when the field charge moves closer to a negative source charge distribution here, okay, the electric potential goes down. The electric potential difference is negative, regardless of the sign of the field charge. Only the source charge counts. We've talked about how to calculate the difference in electric potential between 2 points in space, okay, for a source charge distribution. But what we would ultimately like to do is to be able to assign a single value, okay, for the electric potential at every point in space. Take a look at the title of the slide. How do we go from electric potential difference to just electric potential? Okay, how can we do that? Well, okay, let's look at what we did previously in our discussion of gravity and gravitational potential energy for a clue. So think about what we did in mechanics. Okay, our goal was to assign a scalar function called gravitational potential energy at every point in space. Okay, whereas here our goal is to assign a scalar function called electric potential energy and electric potential at every point in space. How did we do this in the case of gravity? Well, we needed to choose an arbitrary 0 point where we would assume that the value of the gravitational potential energy and the gravitational potential would be 0, okay, at that point. And we could define the gravitational potential and gravitational potential energy of all other points, okay, relative to that point. So we're going to do something very similar here in the case of electricity. Okay, we need to choose an arbitrary 0 point where we assume that the value of the electric potential energy, okay, and electric potential is 0 at that point. So as we saw in the case of gravity, the choice of this 0 point is purely arbitrary, okay, and we ended up choosing really two very common 0 points depending on the type of problem we were solving. Okay, recall in the case of gravity, we very often said when we could consider the gravitational field to be constant, when we're moving objects small distances relative to the surface of the Earth, okay, very often we said that, okay, let's assume that the gravitational potential energy is 0 at the Earth's surface. Sometimes we said it was 0 at the top of a table, but very often we said the Earth's surface, we'd call that the 0 point for gravitational potential energy. In a similar way here, okay, we are going to say that the electric potential energy and the electric potential for an earth ground, okay, or any conductor that is connected to the Earth will be 0. So in a sense, the Earth becomes our 0 point, whether we're talking about gravity or electricity. Of course, the concept is a little different, and we'll talk about what we mean by an earth ground more when as we explore this concept of electric potential. Do you remember that for the case of gravity, for objects on the surface of the Earth, you wanted to lift the book up a few meters away from the floor. You'd say, okay, let's consider the floor of the Earth to have be the 0 point of gravitational potential energy in our problem. But recall when we talked about the motion of satellites, and you're going to move a satellite from the Earth's surface, very far away from the Earth. In that case, the force of gravity could no longer be considered constant, in which case we tended to choose a totally different 0 point, okay, for the 0 of gravitational potential energy. And what we did there is we said that, okay, the gravitational potential energy was 0, okay, for a mass when that mass was located infinitely far away. Okay, we'll say r equals infinity. In a similar way here, okay, for the case of electricity, we're going to do the same thing. We're going to say that both the electric potential energy and electric potential, okay, for a point that is infinitely far away from the source charges, from your source charge distribution, okay, that's where we would arbitrarily set the value of electric potential energy and electric potential to 0. So with a definition of a 0 point for electric potential energy and electric potential, okay, we can now go from this quantity we call electric potential difference to this quantity we call electric potential, which specifies, okay, the electric potential at a single point in space. And so let's say here that the definition of the electric potential, okay, at a point P will symbolize V sub P. Qualitatively speaking, remember, electric potential difference and now electric potential will be the opposite of the work done by the Coulomb force, okay, per unit charge as the field charge moves from infinity, okay, to point P. So quantitatively, we see here that the electric potential at a point is simply the electric potential difference, okay, between that point and infinity, because remember, we define the electric potential at infinity to be 0. So here, given that the electric potential difference is arbitrary, so the electric potential, okay, is defined to be 0 at, okay, a position of infinity, infinitely far away from the source charge distribution, okay, we can now turn a potential difference into just a potential at a given point in space. So you see here in your definition, okay, that you know, we're simply evaluating this line integral here, okay, which is dependent upon the electric field surrounding that source charge distribution. We are moving a field charge, you know, starting infinitely far away into that point P, okay, and by dividing through by the field charge itself, we end up with this charge independent quantity here called electric potential. And okay, we'll say here that, and hopefully this makes sense to you, that if the electric potential difference, okay, is a measure of the electric potential energy difference per charge, then hopefully it makes sense to you that the electric potential at a given point is simply the electric potential energy at that given point divided by the charge. Okay, so nothing earth-shattering here. Because we have room here, I do want to talk briefly about units. Some of the information I'm going to present to you here you already know, but some of it will be new. Okay, so we have introduced a couple new quantities. We better be careful to define the units. So starting with the electric potential difference and the electric potential, okay, the unit is what we call the volt. And, okay, no surprise, that's why we use a V, okay, as a symbol. It's an appropriate symbol, okay, for this quantity. And look, by definition, we said that electric potential difference is a measure of work or energy per charge. So our SI unit, or MKS unit, would be an energy unit divided by a charge unit. So we would have a volt being 1 joule per coulomb. When it comes to, okay, electric potential energy and electric potential energy difference, well, we already know our SI unit is the joule, and you know that a joule, okay, is, okay, a kilogram meter squared per second squared, right? Okay, it's a Newton times a meter. But we also have a new unit. A joule is a rather large unit when you're talking about individual charges. So we introduce a much smaller unit, and you'll see this, so you've got to be familiar with it. It's what we call the electron volt. And it's a little bit strange here, and I got to say, look, an electron volt, it doesn't sound like an energy unit. You might think it's a unit of electric, you know, potential or potential difference, but it is actually a unit of energy, as this definition will highlight here. Okay, the electron volt is simply the energy that an electron will gain or lose by moving through a potential difference of 1 volt. And if you think about this here, okay, the conversion, we're saying that, okay, the change in electric potential energy is simply equal to the charge that is moved through a potential difference, delta V. So if the potential difference is 1 volt, okay, and we move it, in other words, 1 joule per coulomb, and if we move a charge that is equivalent to 1 electron, that is 1.6 times 10 to the minus 19 coulombs, we see here this conversion that 1 electron volt, okay, is equivalent to 1.6 times 10 to the minus 19th joules. Okay, that's a conversion between these two. So you will see this in some of the problems. It's important to know. And finally here, I put this here, electric field, you say, oh, I already know that unit. Yeah, remember the definition of electric field, it was a measure of the Coulomb force per charge. So we know that unit of a Newton per Coulomb. But I'm going to list this one here just so you have it together. You will see why this comes into place later, okay? But it turns out that a Newton per Coulomb is equivalent to a volt per meter. So very often you will come across this unit as well. So you need to be familiar with it. So it can be easy to confuse the concept of electric potential energy with the concept of electric potential. And I'm hoping that with this example problem here, okay, we will highlight some of the differences and hopefully, okay, alleviate some of this potential confusion. So as the problem suggests, you see Bongo over there trying to stick a fork in an electrical outlet. Well, you certainly know better than to go sticking a metal fork in an electrical outlet in your house, because the consequences of a mere 110 volt potential difference between you and the ground could be lethal. Okay, it actually could be very dangerous. But certainly at some point in your life, you've rubbed a rubber balloon on your head. Okay, you've gone down a plastic playground slide, easily generating a 5,000 volt potential difference between you and the ground. Yet the consequences of, okay, rubbing the balloon on your head or going down the slide, okay, were barely noticeable. Okay, certainly not lethal. So to understand why the charged balloon is not dangerous, okay, let's consider some typical data for charged balloons. So I'm making this up, but this is a rather typical value. Rubbing a balloon on your hair and collecting some electrons on it. Okay, you can consider that the balloon would be charged to, okay, about negative 5,000 volts and would have about, okay, a microcoulomb of negative charge on its outer surface. So let's ask some questions here. If I said, what is the electric potential energy per charge on the balloon? Okay, we would say, hey, electric potential energy per charge, that's just the electric potential. That's the definition. Okay, that's what we call the voltage, which is given to you in the problem. There's nothing to figure out. So the electric potential energy per charge is negative 5,000 volts. If I said, what is the total electric potential energy of the charged balloon? Okay, well, this we're going to have to figure out. Okay, and from the previous slide, you see that the electric potential energy is simply the charge times the electric potential. So we're told that this balloon, you've rubbed off a microcoulomb, that is 10 to the minus 6 coulombs of negative charge, okay, and that the balloon itself is at an electric potential of negative 5,000 volts. This means that the electric potential energy of those charges stuck to that outer skin of the balloon is 0.005 joules. So hopefully you can see, why the balloon isn't dangerous. Okay, while it is true that the potential energy per charge, that is the electric potential, is quite high, that number has a magnitude of 5,000, the total potential energy, okay, 0.005 joules, that is quite small. Okay, so you can see the difference here between total energy and the potential energy per charge. Okay, so if I ask you then here, explain why you can safely touch the dome of a Van de Graaff generator that is charged to an electric potential of 50,000 volts, what would you say? Well, the answer is pretty much what we're saying here. It's the same answer, that while the 50,000 represents a measure of potential energy per charge, and that number is quite high. That really means that for a given charge on the dome of the Van de Graaff, that one charge has a lot of potential energy for a typical charge, right? Okay, the potential energy per charge is quite high. Each charge has a fairly high potential energy. Okay, but because there are just not that many charges on the dome of that Van de Graaff, there are not that many charges that could ever get transferred to your body. The total potential energy that could ever get transferred to your body is not high at all. In the same way, the total potential energy that could get transferred to you from the charged balloon is very small in the case of the balloon as well. So you see here, that's what would make something dangerous. So you got to be careful. You know, a number like 100,000 volts seems high and it seems like it could be dangerous. Okay, but in the case of an electrostatic situation, for charges collected on objects like balloons, shoes, slides, it will not be. Last thing I'll say here, consider, since many of you have gone through Physics 102, I kind of like this analogy. When you're talking about thermal physics and you're learning the definition of thermal energy, you may have come across this problem, and I should say you're learning the definition of temperature. I talked about the typical 4th of July sparkler. Those sparks can exist at a temperature of several thousand degrees, which means that that temperature is a measure of the average kinetic energy of those sparkler molecules. And at several thousand degrees, you can say the average kinetic energy is really quite high. But yet, if you've ever held a sparkler and had those sparks come off on your body, you can't feel it. Even though the average kinetic energy of those molecules is quite high, the sparkler is not dangerous because the total kinetic energy that could ever get transferred to your body is really quite low. There's just not that many molecules. Even though any given molecule for that sparkler does have a lot of energy, for a molecule, the total energy is not high at all because there just aren't that many molecules. And that is kind of a similar case to what we have here, when you see that because there just aren't that many charges, the total energy can be small, even when the energy per charge can be quite high. Now, this certainly would have been a lot more appropriate if this was a picture of a Cocker Spaniel named Gabby, but hey, this is the best I could do here.